Okay, let's solve this problem here. 3 kilogram. Okay, so I want you to solve I'm also going to ask you to assume that the collision takes place. Assume collision takes place in 0.5 seconds. So during that 0.5 seconds is where they're colliding. After that, they're either stuck or they bounce off each other. So what would the V final of system be in inelastic collision? What would percent loss of kinetic energy be if it is an inelastic collision? So these two objects are colliding. And then we could also solve what would F average be between the blocks during collision. B. Now solve the same question if it's an elastic collision. What would V of each block be in elastic collision? And then in that case, I'm not going to ask what's the loss of kinetic energy because there is no loss of kinetic energy in elastic collision. But I could ask this question: what would F average be between blocks? Now, before we even do this, I want you to think, in which case is F average between the blocks going to be greater? When two objects collide, they get stuck, their force of contact, okay, versus two objects collide, they bounce off, their force of contact. When is their force of contact greater? Get stuck or bounce off? Bounce off? Why? No, momentum is conserved in both cases. We're assuming that momentum is always conserved in these problems.
It takes more energy to push off or something. It's just like when, oh no, actually, more energy needed for both blocks when they come together. Because if you like drop an egg from a building, if the egg cracks.
Okay. Versus the egg were to bounce.
Actually, the egg were to bounce, take more.
No, I think you're kind of headed in the right place. Imagine as the egg is bouncing, you have a little scale, and as the egg is bouncing on that. Now, would the scale read more if the egg bounces versus if the egg crashes and just breaks? When would the scale read more? Yeah, you got the right idea, yeah. For the elastic, it would be more. In and out, you know, so it should be more. More impulse, more force of contact. Whenever something goes like that, it's coming and going. So it imparts more energy to the other one, and it imparts more impulse, and it imparts more force on the other one, okay? And that's oftentimes what you'll hear karate people say. When you want to break something or hurt something, you go like that more versus going like that, you know? You're able to hurt that person more, you know? You can use physics to do some damage, okay? So that's the idea. We should find that this force is more than this force here. Okay, so let's solve this one. For the part A, they're going to get stuck. So their initial momentum equals final momentum. Remember, we're assuming momentum is conserved. So you have 6 plus 4 is equal to their total mass is 7 times V final. So V final is equal to 10/7. Okay, that's meter per second. So we answered the V final of the system. And then what's the percent loss of kinetic energy? We're going to see that kinetic energy is lost. Kinetic energy initial equals half times 3 times 2 squared plus half times 4 times 1 squared. And that's equal to 6 plus 2, 8 joules. So the initial kinetic energy of the system is 8 joules. The final kinetic energy of the system is half times their total mass, which is 7, times their final velocity as a system, which is 10/7 squared. You see? So that one is going to give you 7, it's going to be 100 divided by 2 is 50 divided by 7, right? 7.14 joules. So the percent loss of energy is not that big here. That makes sense actually because their velocities are close to each other. 2 meters per second, 1 meter per second, because their relative velocity with respect to each other is only 1. If this one was coming at 8 meters per second, this one was 1, I would expect more loss of energy. If they're coming towards each other, I'd expect a lot more percent loss of energy, you know. So those are all the things that you can consider. In this case, then the percent loss should be low. Eight minus 7.14 over 8 is the percent loss of energy. About 11%. Yeah. So about 1 joule of energy goes into making sound and bonding these two blocks. Their bonding energy is not going to be that high, you know. It's not going to be. It's going to be kind of loosely bound to each other. Okay, so that's that. Now, what's the force of contact between them? In order to answer that question, what we got to do is say the impulse, the change in momentum of let's say the 4 kilogram is equal to the impulse imparted on the 4 kilogram. Right? The impulse that the 3 kilogram object imparts on the 4 kilogram object is equal to the change of momentum of the 4 kilogram object, right?